Hey, thanks for joining us for this second video in the NMR series. So here we're going to actually get into more about how to interpret the NMR spectra. Last time, right, I think we discussed how the number of signals tells a really important piece of information, which is how many different kinds of protons are equivalent. Within the same molecule, you could have some of the equivalent protons, right? Like especially if the three hydrogens are on the same methyl carbon, right? They're usually all equivalent and stuff like that. So that appears as just one signal for the three protons. Today we're going to talk about at least the location and the area integration um, aspects of the NMR signals. I should say proton NMR signals. Okay. Now, alkane protons, the regular alkane CHs, right? Those typically show up in the more upfield 1 to 2 ppm, and that makes sense because those hydrogens are just attached to carbons, which are not electronegative much, and so for that reason, those protons tend to be shielded. Remember, shielded things show up upfield, like in a smaller chemical shift ppms or numbers, right? They can be shifted downfield, meaning like higher numbers, higher chemical shifts when you have electronegative atoms attached, and then of course that's because they can inductively through the bonds withdraw some electron densities, and so these are some of the trends, and you notice that this chemical shift is like correlated to how electronegative each atom is. Like iodine is not as electronegative as fluorine, for instance. And I want you to notice how in the bottom row, right, like the effect of these electronegative atoms like chlorine, they're additive. When you have one chlorine, it's about 3.1 ppm for this methyl, but when you have two, it's 5.5, because going from methane to chloromethane, apparently chlorine shifts about 2.1 ppm downfield, and that is multiplied by 2. There's like about 4.5 shift, and then again tripled, again like a 6.3 shift with 3 chlorines. Now those additive effects, it's not always exactly additive, it's not like exact math, but because it depends on other things as well, but it's roughly additive, the impact. I hope that makes sense. And the impact is felt in further down the chain as well, usually like at the beta carbon. So alpha is where the action is, like chlorine. Beta carbon is next to that, gamma will be one more down. At the beta carbon, there might be just a few point 2 or 3 or 4 ppm shift as a result of this chlorine, but by the time you go down on one more bond, the impact is basically negligible. That's what this shows. Like this should have been around 1.2 ppm if it wasn't for this chlorine. Okay. Now, the base alkane shifts are about these, like terminal methyl about 0.9, methylene, by the way, those words are kind of important, that shows up over and over, so please do know methylene is like methyl, except we're talking about the CH2 group, not CH3, and the methine is again a single carbon that has just a single hydrogen on it. Methylene 2 hydrogens, methyl 3 hydrogens. Now, that's the base numbers I want you to know, and that's going to be shifted depending on like what else is going on those methylene or methyl or methine protons or carbons. If the methylene bears alcohol on it, that is again an inductively electron withdrawing functional group, so it shifts the chemical shift by 2.5 due to that oxygen, so we would expect this to be around 3.7 ppm. Now, likewise, when these methylene are on an instead of an alcohol, ester oxygen, I should say, it's about 3 ppm shift. Now, if you're worried you need to know these numbers, you don't necessarily need to for the reasons we'll talk about later, but these couple of examples, it's helpful if you know them off the top of your head. You could do some interpretation much faster. Now, with the when the methylene is next to a carbonyl, that remember, this is a fairly electron withdrawing functional group, right? Because of that, it shifts about 1 ppm. It's not as drastic, you notice, as when this carbon is directly attached to an oxygen, but so you expect this to be around 2 point something ppm. The actual chemical shift is 2.4. These prediction is not always exact because the exact actual shift is dependent on a lot of many factors, but at least these predictions suffice to give us a ballpark prediction of what the chemical shift should be. Let's see if we could predict the chemical shift of all the protons present in this molecule. Let's start from the left side. So this is a methyl group. Remember, the base for methyl is about 0.9, and it's not attached to any drastic functional group, any functional group at all, this methyl group, right? Now, it is beta to this alcohol, and so for that reason, it's probably, in real life, it's a little more downfield than 0.9, like probably it's more like 1.0 or 1.1 or something like that, but still, 0.9 gives us the ballpark value. It's around 1 ppm, that's the bottom line, okay? Now, moving on to this methine with alcohol on it, right, it could be predicted like this. So methine, whoops, I used the wrong number here, I just realized. Methine's base number is about 1.7, so this should be 1.7 instead of 1.2. And when you have an alcohol attached to it, directly, it's another downfield shift of 2.5 in the previous slide. When the methyl, proton is right next to a carbonyl, that even further down shifted by about 1. So if you add those up together, if this was 1.7 instead of 1.2, this should come out to be 5.2. I just happen to know in real life this shift is around 4.7. Again, the technical calculation prediction should be about 5.2 based on what we've said in the last table. Sorry for that typo there. So this really should be 5.2, but like I said, in real life it's probably around 4.7, and it's because of some other factors. But again, that gives us the ballpark. The proton shift for this methine is around 5, is kind of the bottom line. Now, this proton is next to carbonyl. The base for methylene is again 1.2. Next to carbonyl adds 1.0-ish ppm, so we expect around 2.2. Now, in real life, this is probably going to be a little bit more downfield because it's also kind of somewhat beta next to these chlorines. But again, that gives us the ballpark. What about this proton? Well, every time you have an alkyl halide, it's about 2 to 4 ppm, depending on what it is. Chlorine shifts it to 3 point something. In other words, chlorine alone shifts by 2 ppm or so from the base value of methine or methylene. You got 2 of those, and so for that reason, we expect it to be around 5.5. In fact, we saw that value earlier for this dichloromethane. And lastly, this alcohol, because it's a proton on a heteroatom, usually it's hard to predict exactly, somewhere around 2 to 5, who knows. Okay, so that's the prediction. In class, we'll predict the chemical shifts for this molecule together, but another really important tool that I want you to master the use of is this chemical shift range table, which, by the way, this will be provided to you on the exam, which now that does not mean that you don't need to study this table, because if it's going to be the first time you use it during the exam, you'll just have no idea. These tells you like what chemical shift range you could expect for each types of protons, depending on what that carbon is attached to. And there's some abbreviations you might not be super familiar with, like AR just means aromatic ring, and so forth. Let's practice using this table. If you're doing the NMR problems correctly, you should be really busy referring to this table all of the time. Now, let's move on to the discussion about the area under the curve, integration of the signal, what that tells us about the compound, the molecular structure. Now that we talked about the chemical shifts a bit, that the area under the curve, or area under the graph, however you want to think about it, shows how many numbers, how many protons you have of that exact type. Now, when we say area under the curve, this is what we mean. Each peak in the NMR spectrum, if you zoom in, kind of looks like this. So there is an area under this graph, or this peak, or this curve, Does that make sense? So when we say the integration or the area, which are kind of synonymous, that's what we mean. And often in the NMR spectrum, you might see integration trace curve that looks like this. What that is showing you is this is the cumulative total of all of the area under this curve. So up to this point, there's this much area under the curve, and up to like this point, middle of the peak, right, there's this much area under that point, and by the time you're done with the peak, there has been this much area total under the curve. And so this is kind of, if you've taken integral calculus, this might be more easily relatable, but you don't necessarily need to know that. This basically in practice, the difference between the height difference between here and this height is proportional to the area for this peak. Okay, so area under area under the curve or the graph. Why is it important? Because that's proportional to the number of protons. And in real life, this is what it's going to look like. Here's the cumulative integration, and it's like stepwise because this is a triplet, which we'll talk about that a little later. So it's stepwise into 3. This is smooth because there's singlet. This is stepwise into like 6 little peaklets. But this is what it would look like. Now, computer or the software for the NMR doesn't know how many protons each peak has. That is up to you, the chemist, to interpret. So often the integration or area under the curve value might be spitted out by the software, kind of like this. This is pretty typical. You set one of those values to be 1, and then everything else is going to be relative to that, because again, it doesn't know the structure of the molecule. It's up to you to figure that out, right? Now, it's unfortunate that these are not exact whole numbers, because there can only be a whole number of protons, right? You cannot have 1.5 protons, right? Does that make sense? But there's always going to be some sort of a little bit of measurement error, and so for that reason, you're never going to get a super clean numbers, unfortunately. But you can use the ratio to figure out the numbers of protons. So instead of using the previous ratio, if we multiply everything by 2, we get something pretty close to whole numbers for every single peak. So that's likely the actual number of protons. So there's probably 2 protons here, 3 here, 2 here, 3 here. That's how that works, if that makes sense, about the integration. So just to kind of put this into practice, right, see if we can predict not just the chemical shifts, but the integrations for this molecule, terbutyl methyl ether, which is sometimes used as an additive for your gasoline. First, the number of signals we have to decide on. Does it make sense to you that there's 2 signals for this, right? There's these 3 methyl groups that are the same, because this bond can rotate, so that makes these 3. This bond can rotate, that makes these 3 methyl groups equivalent, and each of the methyl groups has 3 hydrogens in it, but each of these bonds can rotate, and so that makes all of these 9 protons equivalent. And of course, this methyl group is directly attached to oxygen, so they would have a very distinct chemical shift. So there's a total of 2 signals. The first signal has the 3 equivalent methyls, 9 hydrogens. And this is basically just regular alkane, right? They're next to only like alkane carbon, right? So we should expect something like 1 ppm for this methyl. Now, the methyl directly on the oxygen, there's 3 hydrogens on it. It's next to oxygen, so it's probably like shifted by about 2.5 ppm from the regular methyl. So we expect something like 3.4, 3.5 ppm. Hope that makes sense. So the proton NMR spectrum that we expect should look like this. And if you took the integration of the actual experimental spectrum, it might look something like this. It's about 1 to 3. It's never going to be exactly cleanly, but it should be something close to 1 to 3. Now you might say, well, I thought there was 3 and 9 protons, right? Remember, the computer doesn't know that you've got 3 and 9 protons. The actual integrations are just ratios, so you have to interpret, right? So there's 3 hydrogens and 9 hydrogens. Then of course, the 9 is upfield. The 3 hydrogens, that's going to be downfield, which is that. Okay. In class, we're going to work on this molecule. And integration, like we said, remember that you could have, you have to think about the equivalency of protons. If you look at this structure, notice that because of resonance, it doesn't really matter where you draw these 3 double bonds. Okay, so for that reason, there's a plane of symmetry right in the middle. So I hope it makes sense to you that these 2 protons are equivalent, and there's also a plane of symmetry right in the middle this way. So these 2 protons are equivalent. All that to say, these 4 hydrogens are in the exact same environment because of the symmetry. And of course, they would be distinct from this methyl group, but because there's a plane of symmetry right in the middle, this is equivalent to that methyl. So, guess how many signals you should expect? 2. Remember, that's the TMS reference. Peak. And this is regular alkane, so that's next to aromatic, so that shifts about 1 ppm. So 2 ppm or so is what you expect. And these are on benzene, so you expect it to be about 7 point something. So these are the 2 signals for that. And guess what the ratio should be? So it should be 4 to 6 or 2 to 3 ratio of integrations. Okay, hope that makes sense. And in the next video, we're going to talk about the last factor of NMR, which is the splitting patterns, as well as carbon NMR.